Okay, so let's move on to dynamics. So let's get out our chart here of old things and new things. So one of our important old things would have been forces. So first we just studied kinematics, all the rules of something moving, but we never explained what would cause something to accelerate in the first place. Well, the first law of Newton says that in order to accelerate something, you need a force. Forces are measured in newtons. Now we have something new. So it is called the torque. So to accelerate something, to make something that was at rest start to move, or something that was already moving slow down or speed up, to change its motion, we need a force. To change the state of something rotating, we need a torque here. So first, let's actually look at this picture on top of this. So when you go to make, like, say, a door rotate, there's three things that are important. The first thing is the force. So the harder you push, the more you will cause that door to rotate. That's kind of obvious. The second thing is what's called the lever arm or the moment arm, or you could just call it the radius. How far out from the door do you push? So the further out from the door you push, the easier it will be to cause it to start to accelerate. And then the third thing is the angle. So we measure the angle, you can see right here. So if you were pushing dead in this way or dead that way, we would measure that as an angle equal to 0. So this dotted line right here would represent 90 degrees if you push straight perpendicular into the door. So when we put those three things together in an equation, we get this torque. And by the way, the symbol for torque is the Greek letter tau. And a lowercase tau looks like this, like a funky T. An uppercase tau looks just like a normal T. But anyway, so that's tau. And to get the torque, we have to take our force multiplied by our lever arm multiplied by the sine of the angle. And remember with sines, sine is a maximum at 90 degrees. It's equal to 1. So the largest the torque can ever be in terms of the angle is if you push dead in. Anything other than that, it's less than 1. And one more really important thing is that if you push right in there so that your angle is 0, like this, then sine of 0 is 0. So you wouldn't have any torque at all in that case. So something they might ask about, imagine, let's bring this circle back up, that this was a wheel, and that we wanted to make this wheel start to rotate. Well, in order to make it start to rotate, if it wasn't already, we would need a torque to change that motion. So let's say you pushed out here. This force would cause a torque, and it would be the product of how hard you pushed and the distance from the point of rotation to where I'm pushing. That's called the lever arm. And it would also matter what angle I pushed at. One thing they like to ask about sometimes is like a wheel going down a ramp, but it wouldn't just have to be a wheel. But let's use that. It's a good example of understanding these. I'll use this mouse pad right here as my ramp we're going down. So let's say our wheel is right here. So gravity is going to be involved in causing this thing to go down the ramp, but it's actually not gravity that causes it to rotate. First off, let's imagine there was no friction. I'll tell you right now that with no friction, it would just slide down without rotating. But when there is friction, we start to rotate like this, obviously, as we roll down the hill. Now, why is friction needed? Well, let's look at these different forces here. So one force on this wheel would be the force of gravity. But where does the force of gravity act? Right here in the center, because that is the average position of all the mass. So if we act right at the point of rotation, gravity cannot cause a torque. Why not? Well, remember what torque is. It's force times lever arm. And if we rotate at the center and the force is acting at the center, we have no lever arm, so no torque. So gravity alone cannot exert a torque on this, and gravity alone cannot cause this wheel to rotate. And that's why if this ramp was frictionless, it would just slide down like this. So that's the first thing. So what's another force on this? The normal force pushes up on this wheel, but it pushes this way. The normal force does not cause a torque. Why not? Well, we sort of already talked about this one, but that angle right here is 0. So when you plug that into this part, sine of 0 is 0, no torque. So it's not the normal force that causes it to rotate, but if there's friction, It tries to slide because of gravity, but friction will scrape it back this way. Friction will have a lever arm from here to here, equal to its radius. There will be a force of friction this way. It will push at the maximum angle, which is 90, which is what we want. And so it is friction that causes it to rotate. And otherwise, in reality, if you had like a really icy hill, you might get some sort of combination of slipping and rotating. So that is how sliding down a hill will work. So let's put these back up here. Now, another thing that becomes important for making things move is the more mass something has, the more it's going to resist any acceleration that this force is trying to cause. And so mass is measured in kilograms. And now we deal with something called the rotational inertia. The symbol for it's capital I, and it's measured in kilogram meters squared, which is weird, I know. But now, how do the two relate to each other? This is an equation I always say you need to know the spirit of. You don't have to have it memorized exactly. How we get the rotational inertia, sometimes also called the moment of inertia, is we would sum up every little bit of mass. And when you take some little bit of mass on a rotating object and multiply it by its radius squared. And if you had another little bit of mass, you'd have to add that in, doing the same process there. Here's the key. The more mass you have, the more resistance to rotating you have, the rotational inertia. And the farther out, the bigger the radius of that mass, the bigger your resistance to rotating. Or your resistance, I should say, not resistance to rotating, your resistance to changes in rotation. So if you're not rotating, the more you won't want to start rotating. If you're already rotating, the more you'll want to stay rotating. So you need to know that mass and radius, where that mass is, affects how much something wants to stay rotating. So let me show you that with this quick example right here. Let's say these are little weights on a wheel, like a bicycle wheel that you have spinning. Or it could be people on a merry-go-round, whatever. So the wheel could have some amount of mass, or sometimes maybe they'll say the wheel has a very light mass that you can ignore. And then you have these weights out here. In this case on the left, they all have bigger radii. And that will cause the rotational inertia to be bigger. So here I have this rotational inertia is much greater than this one. Over here you can see I moved them in. So again, you can imagine weights on a spoke of a wheel or people on a merry-go-round. If you move them in so they have a smaller radius, then that will drop the rotational inertia. So if this was a merry-go-round, let's say, this one would be easier to get spinning, even if the merry-go-round weighed the same and the people all had the same mass. So this one would be easier to start rotating. This one would also be easier to stop. This one would be harder to start rotating, but it would also be harder to stop. And so that is a very important concept in rotational inertia then. And obviously the mass matters too. So if you added mass on there, if you put more and more people on the merry-go-round, it would get harder and harder and harder. One last quick thing here with the dynamics aspect of this. This is Newton's second law, and it is on the equation sheet. So the acceleration is equal to the sum of the forces divided by the mass. This is also on the equation sheet. It's the rotational version of Newton's second law. So the angular acceleration is the sum of all the torques acting on an object divided by its rotational inertia. So if we wanted to get these wheels spinning, we could figure out, and you might have more than one torque. You might have someone pushing this way over here and like out here on this one. And so for each one of those, you would have to find the torque, the force times the lever arm times the sine of the angle. And once you added up all those torques, they will always give you the rotational inertias. If you're studying this on your own, you may see that they give you these big equations for all these different objects and what their rotational inertias are, but you won't have to have that memorized. They will always give that to you. But you could figure out that angular acceleration from summing up all the torques and then dividing by the rotational inertia.